This is screencast number 2 from chapter 6. We will be focusing exclusively on collisions. I hope you've never been in a collision in a car or any other serious collision for that matter. There's an awful lot of physics behind it, but the best way as far as your personal well-being is concerned is to avoid them altogether. I had a collision one time playing softball right before final exam week my freshman year in college, and was knocked unconscious, came to in the hospital with a broken jaw. And they wired my teeth shut by putting braces on. And for 6 weeks, I had to suck everything through my teeth. And my mom said we went through 3 blenders that summer. And I've been in a few car accidents as well. One when I was a boy in our family vehicle. And that was pretty serious, but no one was seriously hurt. The car was destroyed. That God was looking out for us there. And a couple of other times when another car ran into the back of me. In any case, when we talk about collisions, we can have collisions in 1 dimension. Later, we're going to talk about collisions in 2 dimensions, the X and Y directions. We will not be talking about collisions in 3 dimensions, which would be 3-dimensional space. We're also going to talk about the fact that there are 2 kinds of collisions. They can be either elastic or inelastic. So let's focus on those 2 vocabulary words for the moment. We know that the total energy in any collision is going to be constant because energy is neither created nor destroyed. However, when we talk about the total kinetic energy, that is often not conserved in a collision because some of that kinetic energy goes to internal energy. And that internal energy would show up in the form of heat. Some of that lost energy can make a sound, like in a crash. And then some of that will go to the work that is permanently deforming, because it's an inelastic collision, permanently deforming the object, be it the car or something else. So we define inelastic collision as a collision in which momentum is conserved but kinetic energy is not. As we go through this discourse, you're going to see that momentum is always conserved. Kinetic energy is going to be conserved in elastic collisions, but kinetic energy is never conserved in an inelastic collision. Now, one example of an inelastic collision is when 2 objects collide and stick together. Maybe think of 2 balls of clay being thrown at each other, or even a billiard ball or some other ball with a hard surface colliding with a ball of clay and the clay sticks to it. Or maybe there's Velcro or 2 magnets that cause the 2 objects when they collide to stay together. That would be a perfectly inelastic collision. And the word perfectly here we take under advisement, but it is pretty close to being perfectly inelastic. Also, an elastic collision, therefore, is going to be when both momentum and kinetic energy are conserved. Now, that's not generally going to be perfectly elastic, though for a couple of significant digits or places in our calculations, we're going to assume some collisions are elastic, like when 2 billiard balls collide. Of course, when 2 billiard balls collide, they do make a sound, so there's going to be a little bit of kinetic energy lost into sound, and there's always going to be, it'll be hard to measure that because there'll be some energy of friction as the ball rolls across the surface of the felt table. But the main thing to remember, in elastic collisions, momentum is conserved, but kinetic energy is not. In elastic collisions, both momentum and kinetic energy are conserved. Most situations are going to be somewhere in between. And these 2 boxes here summarize the things that I was just talking about. Now, when we have collisions, those collisions are probably going to release a little bit of energy. For example, I mentioned the clicking sound when two billiard balls collide with each other or a basketball bounces off the floor. However, when we are looking at atomic and subatomic particles, right here, we can consider those collisions to be elastic. Most actual collisions fall in the range between these two. Now here's a practical application in this paragraph. If you've ever been to the eye doctor, and I go to my eye doctor every other year, and they do a glaucoma test where they take a little puffer that shoots out a puff of air, tonometer, measuring the tone, if you will, of your eyeball. And it puts pressure on the eye. And if the eye is healthy and there's no glaucoma, then it bounces back. The eye is slightly spongy. And so as a result, the sound wave is going to come back at a lower speed. However, if there's an awful lot of pressure inside the eyeball, which is a symptom of glaucoma, which can lead to serious eye issues like blindness, the speed when it bounces off, the speed of the air, I should say when the air hits the eyeball and that energy is transferred to the back of the eyeball and bounces back again, it comes back much faster. And so the speed of the reflected puff of air can measure the internal pressure of the eye. And the faster the speed, the greater the pressure, and that would mean that would give you an indication as to the extent to which you have glaucoma. At this point, you could pause the video and do your quick quiz. And now let's take a look at perfectly inelastic collisions. Again, kinetic energy is not conserved. So we can say that if I have two objects colliding with each other, and this is going to be one-dimensional in a straight line, you have the momentum of the first object, and it collides with a second object. They could be head-on, or one object could catch up with the other object, or one object could be stationary and the other could be moving. In any case, when they stick together, we combine their masses. And notice that we have an initial velocity for one object, an initial velocity for the other object, and a completely different velocity for the two objects when they've stuck together. So that this equation, if you simplified it, would enable you to find the final velocity of the two objects that have stuck together. I would not bother to memorize this because it's pretty easy to set up the math here with conservation of momentum and solve it from there. As an example, take a look at the picture over here on the side. Here we have a smaller ball traveling to the right, a larger ball traveling towards the left. They have different speeds. We are told that the speed of the first ball is greater because you can see this vector is maybe twice as long as this vector. I don't know if the mass M2 is twice as much as mass 1, but we're going to assume, based upon what comes next in the picture below, that there is more momentum on the left side with the blue ball than there is on the right side with the beige ball or whatever that color is. So that when these two strike together, the combined masses move in the positive x direction, indicating which ball originally had the most momentum. And they have a completely different velocity than either ball had in the first place. This is in one dimension because we're only looking at it in a straight line, which we can call the x-axis. So let's imagine we have a collision between a truck and a car. Kind of looks like a Prius or something there in the blue. But in any case, you'll see that the pickup truck's mass is greater than the compact car's mass by a factor of 2. And you can see they're both traveling at the same speed, but the negative sign indicates that one vehicle is traveling in the opposite direction of the other. And typically, since we read from left to right, we think of the right side as being positive and so anything moving in the opposite direction is negative. So we have three problems to solve here: to find the speed of the entangled vehicles, that means they've stuck together, find the change in velocity of each vehicle from what it had originally before collision to what it has now when they're stuck together, and then find the change in kinetic energy of the system. And that change in kinetic energy would be the energy lost due to heat, deformation of the vehicles, and the sound that is produced in the crash. So, taking a look at our math, we begin with the law of conservation of momentum. P, remember, stands for momentum. My initial momentum equals my final momentum. And we have two objects. So we have the momentum of my truck plus the momentum of the car before collision. And when they stick together, we have their momentum after collision with their final velocity. And now we plug in our numbers. And when we solve for a final velocity, we see that both vehicles are moving to the right, stuck together at a speed of 5 meters per second, substantially slower than the speeds they had originally. Now when we go to part B of the problem to find the change in velocity, for my truck, my original speed was in the positive direction, right here, and my final speed, so this is my final minus my initial. The negative sign is not the result of going left or right. The negative sign here means that we're doing final minus initial to get my change in velocity. And we end up with a negative 10 meters per second. Again, this negative sign does not mean the truck is moving to the left, but it means that its change in velocity went from 15 down to 5, and that's a loss of 10 meters per second. Meanwhile, the car had a negative 15 meters per second originally because it was traveling to the left. And so when you take the initial minus the final, your minus a negative gives you a plus sign. And so you see that the change in velocity for the car, this is the truck, this is the car, went from negative 15 all the way up to positive 5. And on a number line, if this is 0, and here's my negative 15, and here's my positive 5, you can see that that difference there is a change in 20 meters per second. Now, letter C, find the change in kinetic energy of the entire system. So what we're going to do is we're going to first of all find the kinetic energy of my truck and my car. So here's the kinetic energy of the truck right there, 1/2 mv squared. Here is the kinetic energy of my car right down here. And notice that because the car's speed is negative, but we're also squaring the velocity, the negative squared gives me a positive value. So in a sense, we're adding the absolute values of the two kinetic energies, and we're getting the total energy of almost a little more than 300,000 joules. Now, the kinetic energy after collision, when the two vehicles have stuck together, is 1/2 of their combined mass, and they're moving at a speed of 5 meters per second. And so here we get 3.38 times 10 to the 4th. This was 3.04 times 10 to the 5th. And therefore, if we subtract, this right here is the amount of energy that was lost when the two vehicles collided and stuck together. And your remarks here reminds you that the most important safety feature of any car is its mass, which is why one of the downsides of trying to make cars lighter and lighter and using composites and things like that in order to reduce the mass so that you can improve the gas mileage. So your gas mileage might be going up, your miles per gallon, but the danger to the occupants is also going to go up. And that's why we need to take other precautions to compensate, like airbags and the design of the vehicle and collapsible front ends and things like that. Now, this next problem is one of those classic physics problems. And if a physics teacher say it's a classic physics problem, it's a good chance that you might have something like this on a test. And the ballistic pendulum is a device that enables us to measure the speed of something very, very fast, like a bullet. And believe it or not, in about the third year of the school, we had just purchased an old elementary school in Des Peres, and there was a part-time physics teacher who was a seminary student, and he actually brought a gun to the physics class and shot the gun into a block, just like you see in the picture here, so that they could measure the speed of the bullet. Obviously, that's not something we're going to be able to do anymore. But you can purchase devices like this and accomplish the same thing. But of course, you're not going to be firing a bullet from a gun. Now, the trick to this problem, and you better remember this, is we're going to work backwards. We're going to work from what happens after the bullet has already penetrated the wooden block and calculate the energy that it now has when the block swings from this level, the bottom of the block, to up to this level, when it increases in height by the amount h. It's going to increase in potential energy. So we're going to say it has 0 potential energy when the block is hanging vertically, and then as a result of the bullet embedding itself in it, the block swings upward like this, and now it's at a height h, and now it has more potential energy. It has some mgh. Now again, we're assuming no friction up here, no elasticity, no air friction, anything like that. And we're going to do this in order to find the velocity, the original velocity of my block once the bullet penetrates it. And then we can use that piece of information in part 2 of the problem in order to find the velocity of the bullet. So we're going to use conservation of energy, which is the last half of the problem, but we're going to look at that first. And then we're going to use conservation of momentum, which is the first part of the problem in terms of what happens, but we're going to do that last. So, as far as kinetic energy is concerned, when the block is just hanging vertically, it has no potential energy, which is why I said the potential energy goes to 0, because we're using the level of the block when it's just hanging there as our ground level, so to speak. It only has kinetic energy. When the block swings up and stops moving, now it has 0 kinetic energy, as indicated by that. So basically, my formula boils down to kinetic energy equals potential energy. My kinetic energy is 1/2 combined mass. Don't forget about that, because the bullet has just penetrated the block. So it's 1/2 mass velocity squared of the system, the bullet block system. And when the block swings all the way to the top, now it only has potential energy. Again, the combined mass times gravity times height. Now what you'll notice right off the bat is the masses cancel conveniently. And so when we solve this equation for v squared equals 2gh, it looks just like one of our kinematic equations way back in chapter 2, and we can solve for the velocity of the block bullet system, and it comes out to be almost 1 meter per second, 0.990. Now, this is the first part of the problem, but it's the second half of what happened in the ballistic pendulum experiment. Now we're going to take the information, 0.990 meters per second, and bring it down to the second part of the problem, which is what happens first in the ballistic pendulum experiment. And we're going to have our conservation of momentum. The momentum of the bullet and the block, to start with, equals the momentum that the system has afterwards. So here we have the momentum of the bullet. I can call this the BU for the bullet, And here we have the momentum of the block. I'll call that BL, short for block. And of course, this goes to 0 because the block has no momentum. It's just hanging there. So only the bullet has momentum. After the bullet penetrates the block, now we have their combined masses and the velocity of the system. Well, the velocity of the system we just calculated in the first part of the problem. So when we go to plug our numbers in, we have our combined mass. And make sure you remember that if your bullet is given to you in grams, which it was, and the block might have been given to you in kilograms, you need to be consistent. So make sure you convert the grams into kilograms by dividing by 1,000. Kilo means 1,000. That you should know that, but every year there's a student or two that make that simple mistake. And now we just solve for the initial velocity of the bullet, and we find it's traveling almost 200 meters per second. A ballistic pendulum. All right, please note again that energy is not conserved because when the bullet penetrates the block, there'll be a little sound, but certainly there'll be a lot of heat generated as the bullet comes to a halt inside the wood. And there might be some deformation of the wood as well. And here's a good time to pause the screencast and see if you can do the quick quiz. Again, the answers are in the back of the book. Now, what about elastic collisions? We're going to look at elastic collisions in 2 dimensions right now. In a later screencast, we'll focus on elastic collisions. We're going to look at elastic collisions in 1 dimension. Later on, we'll look at elastic collisions in 2 dimensions. So, because of the fact that it's an elastic collision, we know, whether it was elastic or not, that momentum is conserved. But because it's elastic, or nearly so, kinetic energy is also conserved. So you have the momentum before equals the momentum after. The kinetic energy before equals the kinetic energy after. Now we have these 2 equations and we're going to put them together. Up here we can cancel out the halves, and then we can factor out the masses right here in this step right here. And then if you remember this from, 9th grade or 8th grade algebra or something, x squared minus y squared, when you factor that, you get the component x minus y, or the factor x minus y times the factor x plus y. And that's what we get in equation 612. And then we continue to simplify this when we put the 2 equations together, and we get this equation down here, equation 6.15, that shows that my initial velocity minus of my first object minus the initial velocity of the second object equals the negative sign times the same difference, except the initial velocity, the final velocity of my first object and the final velocity of the second object. So the difference in their initial velocities equals the negative of the difference of their final velocities. And that is a helpful identity to solve perfectly elastic head-on collisions. Another way we can say it is this: the relative velocity, that is comparing the one velocity to the other initially and the one velocity to the other finally, the relative velocity of the 2 objects before collision equals the negative of the relative velocity of the 2 objects after collision. And here's a little example, something that Einstein might do, for example, with his thought experiments. Imagine that you're on the one object moving, let's say, to the right, that you're an observer, not contributing to the object's mass, but you're observing and you're moving along and you see the other object coming towards you. In your view of the collision, from the perspective of the object that's moving to the right, the object that is coming towards you, we'll say it's moving to the left, it bounces off because it's elastic, and it leaves your object after the collision with the same speed that it had coming in, but the opposite direction. You might remember that device that has the 5 balls, the 5 silver balls, and you lift one up, and it causes this ball to go up. That's a conservation of momentum demonstration. Now, a lot of times physicists use the game of billiards or pool to demonstrate these kinds of things. So the billiard balls all have the same mass, including the cue ball. And they say, let's say that you have 2 balls that are moving and they're going to collide in a perfectly elastic collision. The one ball, we'll say it's traveling to the right, 30 centimeters per second. The other ball is traveling to the left, note the negative sign, at a slightly slower speed. Maybe it bounced off a cushion or something, and it's negative 20 centimeters per second. And they're going to strike head on. Not a glancing collision. That's something we'll look at in the next screencast. In any case, we know that their momentum is conserved. So we have the initial momentum of ball number 1, the initial momentum of ball number 2. They collide with each other and they bounce apart, each having a different momentum than before. And so when we plug our numbers in, after we cancel out the masses, because the masses are all the same, we see that the object, the first object, now has a speed of 10 centimeters per second. And then when we come down here, let me rephrase that. We see that the sum of the speeds of the 2 balls, the sum of the speeds of the 2 balls is 10 centimeters per second. Now, if we apply the conservation of energy, since it's an elastic collision, and again, the 1/2s cancel out, the masses cancel out, and this is from the equation that we just talked about 5 minutes ago, and we plug our numbers in, we see that the difference in the 2 velocities after collision is 50 centimeters per second. So the sum up here, the sum is 10, the difference is 50. Solve the 2 equations simultaneously, and we find out that ball number 2 that originally had 20 centimeters per second speed going to the left now has 30 centimeters per second going to the right. And ball number 1 that originally had 30 centimeters per second going to the right now is moving towards the left, the negative direction, at 20 centimeters per second. In other words, they swap velocities. They exchange velocities. Now, the last problem we're going to look at in this screencast, example 6.7, 2 blocks and a spring. We have on a horizontal surface. The horizontal surface, we're told, is frictionless. We could add friction into this problem by adding in, by knowing the coefficient of friction and recognizing that some of the energy is going to be lost in the friction. But in any case, we are given the mass of M1, the smaller brown box, right here. We're given the mass of the larger box, pictured in blue. We are also told the speed of the brown box is 4, and the speed of the blue box moving in the opposite direction is 2.50 meters per second. So we want to determine the velocity of block number 2 at the instant when block number 1 is moving to the right with a velocity of 3 meters per second. And let's see, and then part B, find the compression of the spring at that time. So the one block is going to compress the spring, and the spring is going to absorb the energy. So finding the velocity when block number 1 has a velocity of 3 meters per second. Here's our equation right here. We solve it for the final velocity of the blue box, M2, and we find its final velocity is a negative 1.74 meters per second, meaning it's moving to the left. Then, to find the compression of the spring, we're going to look at our kinetic energy. So we have all the kinetic energy of my block that is moving to the right, the kinetic energy of the block that's moving to the left. Notice that even though its speed is negative, the negative speed squared gives me that positive value. The spring has no energy stored in it. That's why that's 0. And then after the collision, my brown box has some speed, my blue box has some speed, and therefore they both have kinetic energy, and there's also kinetic energy stored in the spring. And now we plug our numbers in, and again we have to put our, this value came from up here, and we see that the spring gets compressed 0.173 meters. And next we'll look at glancing collisions, which would be 2 dimensions.